Good evening. My name is Kayla Engel, and this presentation is about color integrated symbolic representation as cognitive support in STEM learning. The core idea is simple. Sometimes students struggle because the concept is too advanced, but sometimes the structure is just not visible enough yet. STEM learning asks students to move through symbols, notation, procedures, and abstract meaning all at once. For students with symbolic processing difficulties, that can create unnecessary cognitive load. This project looks at whether visual scaffolding, especially consistent color integration, can make symbolic relationships easier to access without simplifying the academic content. The instructional problem is that symbolic systems are often presented in a flat, monochromatic way. Students may understand parts of the concept, but still lose the relationships between symbols. So, this study focuses on design, how the presentation of symbolic information may shape access, navigation, and conceptual understanding. This is the shift I'm interested in, moving from symbolic density to symbolic accessibility. The goal is not to make STEM easier in a watered down sense. The goal is to make the relationships more perceivable so students can spend less energy finding the structure and more energy working with the concept. Here, the color is assigned by conceptual role. Green tracks values or results, blue identifies objects or systems, purple signals transformation or scale, aqua marks structure and accumulation, orange shows process or modification. The important piece is consistency. Color becomes a relational map, not decoration. These examples come from different STEM areas, but they ask students to do similar kinds of symbolic navigation. They have to track what is being measured, what is changing, what is grouped, and what process is happening. Color gives those rules a visual anchor. So let's just focus on the statistics equation in its original monochromatic form. All symbolic components compete within the same visual field. The equation remains readable, but for a student already using extra effort to process symbols, that lack of visual structure can matter. But now the math is the same. The pathway is easier to see. The color separates the symbolic roles, so the learner can follow relationship instead of decoding everything from scratch. The structure did not change, the visibility changed. And this is where the idea becomes even more powerful. The same color structure can connect symbols to language. Instead of the equation and the explanation living in separate systems, the relationship carries across both. And this is also where AI matters, because AI could help maintain that consistency across notes, examples, study guides, and digital tools. So, across STEM, students often encounter new symbols before they recognize familiar patterns. Color can help reveal that some relationships repeat across disciplines. The surface language changes, but the underlying navigation demands are often similar. So this becomes this. This is the movement where the design argument clicks. Students are not just seeing isolated equations, they are now seeing recurring relationships. And that matters because symbolic accessibility is not only about reading the notation, it is about recognizing how meaning is organized. The purpose of this study is to explore how color integrated symbolic representation may support symbolic accessibility in STEM learning. Introductory statistics serves as the focused implementation site because it gives a bounded environment for looking at symbolic navigation, conceptual organization, and cognitive accessibility. The main question is how students experience color integrated symbolic representation compared with traditional monochromatic formatting. I am especially interested in how color affects symbolic navigation, conceptual organization, and perceived accessibility within statistics tasks. The key terms are color integrated symbolic representation, symbolic accessibility, cognitive load, and mathematical processing difficulties. Together, these terms keep the project focused on access to symbolic meaning, not just performance or preference. The literature connects four main areas: cognitive load and working memory, dual coding and visual processing, neurodiversity and symbolic systems, and visual scaffolding in STEM learning. Together, these support the idea that how information is structured can affect how accessible it becomes. This study is really an initial implementation study. The goal is not to prove some massive universal effect yet. The goal is to see whether students interact with symbolic information differently when the relational structure becomes more visible. Participants would work with both monochromatic and color integrated symbolic materials within introductory statistics examples. Data would come from reflections, observations, and instructional artifacts, showing how students navigate symbolic relationships under different presentation conditions. The participant group focuses on secondary students who experience difficulty tracking dense symbolic information and self select for the study. The project examines how students respond when symbolic relationships become more visually structured. I anticipate that color integrated supports may improve symbolic accessibility, conceptual organization, and navigation. The strongest findings will not be that color magically solves the problem, but it may be that consistent visual structure gives students another pathway into the symbolic system. For instruction, the implication is practical. Small design choices can affect access. If color helps students track symbolic relationships without reducing rigor, then teachers, curriculum designers, and digital platforms have a low cost way to support more inclusive STEM learning. The study is limited by sample size, setting, and scope. It focuses on introductory statistics, so it cannot claim to represent all STEM contexts. It is also exploratory, which means the purpose is to identify patterns and possibilities for future research. Symbolic accessibility matters. When structure becomes visible, students may have more room to think conceptually. Color integration is not about making STEM decorative, it is about making relationships easier to perceive, follow, and use. These sources for this proposal draw from cognitive load theory, dual coding, mathematical processing, neurodiversity, visual scaffolding, and multimodal learning. Those areas together support the need to study symbolic accessibility as an instructional design issue. Thank you for your time and consideration.